Good afternoon. It's 1 o'clock and it's time to start the last part of the webinar series, Performance Optimization of Scientific Software. The third and last part is called Improving Application Scaling. So we're going to address how to improve the scaling of MPI-parallel codes. So my focus will be mostly on codes parallelized with the message passing interface and how to run efficiently them on the supercomputer platforms. And like we've been discussing on the optimization of the serial performance, before really doing anything, we need to understand and analyze what's the bottleneck for, well, in this case, scalability bottleneck. And again, as in serial part, the idea is not to optimize as you go, but really implement something, getting something to run right in as a parallel application to that you get the same results as you would get from a serial application. And then once you are done, the idea was to go through the code optimization cycle and identifying the bottlenecks and trying to improve the part or the part where the code doesn't scale anymore and try to reach a bit further with the scaling and the MPI scaling. So we discussed this on the first part. So what kind of fingerprints you would like to see from the performance analysis data? And typical thing is that if you look at the profiles, in fact, the computational routines have been, when you double the amount of cores, the computational routines, so the real work has been in fact scaling up. So they've been reduced. The time spent on those routines have been scaled down by perhaps a factor of 2 or something. But then again, the total execution time is not reducing because of the MPI time spent on MPI is blowing up. So basically, it can be due to that the MPI time is indeed increasing. So factually increasing because of the communication is increasing as a function of tasks. So the amount of messages is not constant, but it's really increasing while you increase the number of tasks, and then you run into a situation where the most of the time on this code is being spent on communicating rather than computing. And a typical case or kind of an special case of this is that you hit on expensive collectives like MPI all-to-all or MPI all-reduce and so on. And that's something we're gonna take a look later on in this webinar. So how to perhaps do some minor tricks to improve on this one. Also, it can be that you just run out of things to compute. So the MPI time is not in absolute sense blowing up, but the proportional time is just like becoming too expensive. So the code just stops scaling. And it's kind of a natural point of scalability, and there's not much you can do anymore with the given problem size, with the given algorithm, with the given implementation. So that's kind of the hard scalability wall, and it's a kind of a natural state of being. So you don't have to do anything. And but still, you could think of if you can continue with weak scaling and see if the weak scaling behaves as it should. And another signature of fingerprint from the performance analysis data is that in fact not the MPI communication time per se, but the synchronization time is increasing while as the core count increases. And this is a pretty clear hint on something called load imbalance, meaning that MPI tasks are not equally busy. So some tasks have an imbalanced role. And so your task is to look further whether the tasks some tasks are communicating more than the other ones. So the imbalance is just because of a construction. Perhaps you have some issues in balancing the computation, so some tasks are just computing more than the other ones. Or there's some additional duties for some tasks like doing I/O, and those all will sooner or later give rise for load imbalance and therefore sort of a stop of the scaling. And these are something that should be addressed when, or something that can be and should be addressed when trying to scale up codes. And this is the first. So let's talk about that first. From the data, okay, so you think it's due to imbalance. So find the root cause for the imbalance. So also the measurements can be misleading in some cases. It may look like that you are in fact communicating too much, but you have to be sure what's really the root cause. Why additional measurements and different kind of tests. So whether you would like to see whether it's due to the imbalanced communication, or some additional duties. Perhaps looking at source code, perhaps making more measurements. And the root cause for the imbalanced communication is communication design. The root cause for imbalanced computation is inherently imbalanced work share, meaning decomposition. And of course, if some tasks are supposed to do additional things like printing something to the screen or to the standard error, that will pretty soon yield heavy load imbalance. So meaning that I/O is a very typical scalability bottleneck. Even if it's very innocent, just printing something to the log file will give a rise for load imbalance pretty soon. And well, in order to scale up codes, you have to bite the bullet and be ready to address this. But unfortunately, there's no kind of typically there's no kind of low-hanging fruits here. But you need to dive deeper into the code, perhaps doing some restructures on decompositions, data structures, communication design, and so on, in order to fix the load imbalance issue. Even go even deeper down for what kind of an algorithm are you using. And the codes that want to scale up very high is that you may need to implement pretty complex parallel programming things like dynamic load balancing, meaning that on the go, during the execution time, you have some kind of a measurement for the load balance, and then trying to shift the decomposition during the runtime. It's a pretty complicated thing to do, but sometimes needed in order to keep the load balance stable. Or do this kind of a multiple data style programming, that the tasks are really doing different things via MPI communicators. So there are really dedicated I/O ranks, dedicated nodes for doing some computation, while some other tasks are doing something else or some other part of the computation. So these are the complications of the parallel programming, and sometimes when aiming at high core counts, this is something that just have to be done, unfortunately. But in addition to these, so really heavyweight restructures, there's something that we still can do perhaps on a more limited effort, and that's some kind of how parallel programs should be nowadays being written, and it's about hybrid programming. So the current hardware, how the supercomputers are being built now and in the next generation of computers, the natural or kind of or the close to hardware model, programming model is hybrid programming, where you combine shared memory programming with, say, OpenMP typically inside a node or some subdomain of it, like half of the node or so, and then doing message patching only between these two OpenMP regimes. And the idea is that you reduce the number of MPI tasks and thereby giving less pressure for load balance. So it's easier to load balance, say, 256 MPI tasks as compared to the number that's like a 10 times more, or if you run 10 threads per an MPI task, it's much easier to load balance over 200 MPI tasks than 2000 MPI tasks. And with some luck, it can be doable, in fact, with quite little effort. So if you are in the situation where you have very heavyweight hotspot loops in your code, just like putting OpenMP or using OpenMP only within those will give you an hybrid code, and you may outperform the flat MPI in a little effort. But however, in many cases, in fact, pretty large portions of the code has to be hybridized in order to outperform MPI. So, but and it requires coding, and also with the ready code, it's also needs experimenting with what's the best threads per task ratio. There's a lot of minor considerations, so how the thread affinities are done and so on. But the take home here is that in order to really go to the very high core counts, this is something that typically one needs to be ready to be tackling in order to get there. So, like I said, this is the program model for the supercomputers of today. So really worthwhile of investigating when having an aspiration of improving the scalability of an MPI-parallel application. And so these were the kind of major revisions of a code. So redesign on code redesign on say data structures, algorithms, communication patterns, and so on, as well as the OpenMP plus MPI hybridization. So these are the major things, and that really requires effort, but also typically have an impact on the scaling. But then I thought of going through sort of a minor considerations that may impact the performance. So giving performance improvement or scalability improvement, but doable with smaller effort than these ones that we discussed so far. And these are kind of an idea is to reduce the overhead from the parallelism by doing some minor tricks. And let's walk through this. So perhaps of this, the most important trick is to understand that the MPI ranks, it doesn't matter how the MPI ranks go to the machine. And typically on a supercomputer, when you submit a job, you just get a set of nodes. They may be wherever on the code. So if you wherever on the machine. So for instance, SISU is a 9-cabinet system, so it's 18 meters of length, so it's a pretty big device, and the interconnect is also non-heterogeneous. So you may get one node from the first cabinet and another node on the last cabinet and something from the between. And so the ranks are definitely not, the access from a MPI rank to another is definitely not homogeneous. So some ranks are definitely closer in terms of cheaper to communicate than the some other rank. And this is not only a Sisu or Gray XC thingy, there are all interconnects have an all the interconnects have an heterogeneous access if you go to a large number of nodes. For instance, on the InfiniBand machines, when you start going over switch, you start losing performance on a pretty rapid fashion. So the InfiniBand is fast basically on only within those InfiniBand islands. And this implies that rank placement does matter. So, and the optimization trick is to place the ranks that communicate the most to the same node. So, simple example, if you have a code that does just nearest neighbor communication, just make sure that most of the nearest neighbors are on the next node, and those who run after node goes to the are in the same node, and those who the next rank which that doesn't fit on the node anymore goes to the node after that one, and so on. So typically on MPI applications, the communication is not all to all the time, but there are some ranks are communicating more than the other ones. So the idea here is to try to optimize on that matter. And luckily, this is very easy to do because the system supports this pretty well. You can change the rank placement via a single environment variable that you just put your patch up script. And all MPI libraries supported on Sisu. It's done via variable mpich rank reorder method. So if you look at man MPI, you see how to do it. And for the optimized rank placement, so which ranks should go to the same node, there's a good tool, the GrayPath, that does the performance analysis, is able to it does some simple optimization on the measured communication patterns, and then suggests rank placement that should be better than the default one. And it's so easy that it should be tested with basically every application that are run in a heavy-duty fashion. And well, the example was based on Sisu, but all systems are able to are able to do the rank replacement to the in an optimal manner. Just consult the documentation of the system you are using. Then perhaps minor considerations or having less impact by perhaps default is that you can write MPI in many ways to do the same thing, and there's some good practices for what comes to MPI. So a couple of those in the following. So when doing point-to-point communication on MPI, always resort on the non-blocking. So the I receive, I sends instead of receives and sends, and such that you first of all open up the I receive calls before doing the iSends. So you have the receive open when the send is being posted. And also the non-blocking communication operations allow also for the trying to overlap the communication with some computation. This of course requires code modification, but there may be a chance for it. Typically not extremely important, especially on the XC architecture, but something you can get some benefit out of it. And also another thing comes to the point-to-point communication is that there are two on XC. There's two transmission protocols on MPI called Ether or Rendezvous. where the echo is optimized for small messages and renderable for large messages. And the large messages won't allow for overlapping, even with non-blocking communication operations. So if you want to do overlap of big messages, you have to increase the threshold where the protocol change takes place. And on XC, it's then via environment variable in which Gemini max each message size. So again, man MPI to see what can be changed. And one thing I mentioned in the beginning, so if you can see this from the performance analysis data, and you think of that the reason for non-scaling is in fact expensive collectives like MPI also, that there may be some things you can then do here. Well, the first and foremost is that if you bite the bullet and start hybridizing the code, so this is also where the hybridization is likely to help, because you just like run smaller communicators in MPI. And in terms of MPI programming, see that if you could implement these vector versions, so MPI all to all V and so on, with the basic version, so MPI all to all, even if you would be receiving unreferenced data, because that just sort of reduces the bookkeeping and the simplifies the communication pattern what the MPI needs to do. And also, if you are doing all to all V's, and so the good consideration is to see what kind of and how much data is being sent to the different processes. And if it turns out that all V's is sending 0 messages to, or sort of just doesn't send any data to some of the, or many, or like a large portion of the ranks. So this is something you in many codes you do encounter. So in those cases, point-to-point communication may outperform the collective operations, whereas of course the rule of thumb is that using collectives is a better choice to hacking with point-to-point operations. But in this case, point-to-point operations may be an optimization trick. And also in collectives, the MPI tree, the non-blocking collectives that were introduced in the MPI tree, so MPI I also all and so on, are typically the better performing option to the the blocking collectives, because they, for instance, allow for overlapping collectives with other operations. So you can start the collective in the background, do something, and then wait for the collective to finish, perhaps computation, IO, other communication, and so on. And even if you don't do the overlap, it may be still a faster choice for the blocking one. And the replacement is trivial because the syntax is just the same. You just put the capital I there and add the weighting of the collective. And also there's some parameter environment variables on the MPI library that can be tuned for improved collective performance. So again, one MPI and see what is there. So for instance, one parameter that typically may have some impact is the how to all is being implemented. So what's the message or algorithm threshold for between short and large messages? The last topic of the last topic of today is to address parallel IO or IO bottlenecks, because in many cases it really turns out that the scalability bottleneck is not at the end of the day it's not in MPI, but in fact it's on related to I/O. So optimizing the file I/O is of utmost important for making scalable applications. And the long story short, if you do not parallelize your I/O, so meaning that if you let one single rank to carry out the file I/O, it will be a scalability bottleneck in every single application, period. So in order to have a really real parallel program, you have to parallelize your I/O. And there's a lot of the options vary from just using MPI-IO or doing handwritten schemas where you communicate things and then write to a disk, to high-level I/O libraries like HDF5, NetCDF, and so on. So that's the sort of first and foremost consideration. So serial I/O will be always a bottleneck, and in order to reach core counts beyond some trivial 4, 8, 16 MPI ranks, you have to resort on parallel I/O. And sort of a bit more advanced consideration is that you could try to hide the I/O by moving from a scheme, for instance, where you compute something, dump it, compute something, dump it in this kind of a better focused fashion. You could be having a scheme where you compute, and once this dump off takes place on a certain among a certain set of MPI ranks, the rest of the ranks may still start computing something new part of it, and so this of course gives a raise for an improved overall execution time. And even if you don't want to go into this regime, there's one thing, important thing for basically everybody using SPC systems is that the Lustre or the file system parameters do play a major role in application performance. So there's a command called LFS that sets the Lustre settings. So over how many of these Lustre boxes file is being spread over. So the default on SISU is just putting into one of those object storage targets, but you can stripe them over several of those. And this is just by set on a command LFS set stripe. Just see how many OSDs you want to stride over, and then the name of the directory or changing the parameters. And finding the best striping, which is depending on the file size or the I/O size, how many writers are there, how big core counts are you using, how many files are you writing at the same time, and so on. But they have a big performance impact. So for instance, on SISU measurement, if writing some kind of an intermediate size file, so ranging from 1 to 6 gigabytes, if this is the default I/O speed is somewhere below 1 gigabyte per second, so 700 megabytes per second perhaps. But just with putting one Unix command, LFS stripe -c equals to 4, or -c4, and the name of the directory I'm writing to, the performance with large enough file sizes may be more than a factor of 2 faster. And also, if you keep on increasing the Lustre striping, so again with large enough file sizes, there's a huge difference. So there's a factor of 5 at least, or more, between striping over just to the default one and having stripe factor of 24 here. So in order to get the full bandwidth out of the Lustre file system, you have to stripe over many of those OSDs. And again, there's no kind of a very solid rule of thumb here, but it's so much dependent on the file sizes, number of writers, and the number of files being written at the same time that it needs to be experimented a bit. But the take-home message here is that the Lustre striping set by this LFS command has a huge impact on the I/O performance. And in many cases, the I/O performance is something that is immediately visible on the volume performance. So the summarizing what's been addressed here, the typical considerations for improving parallel application scalability include, fixing the load balance via the decomposition and so on. And while the load balance is established really at the algorithmic and data structure level, we can do something still. So, for instance, one thing mentioned was this rank placement that sort of that helps in the overall application performance by reducing the parallel overhead and also hopefully improving the load balance. And for what comes to load balance and collectives, the hybrid programming, so doing OpenMP within MPI threads, MPI tasks, OpenMP threads within MPI tasks should be the program model of the supercomputers of today. And the idea is really that this typically improves load balance and helps with bottleneck collectives. Minor considerations that you can do MPI in many ways, but some ways are better than others. So the typical thing to bear in mind is that the non-blocking communication is the typically the better way of doing both point-to-point and collective operations. And the last but not least is that many scalability bottlenecks at the end of the day, they boil down to the I/O bottlenecks, so file I/O, and meaning that all file I/O needs to be parallelized, and even when using parallel I/O, the performance is pretty sensitive to the platform, like the Lustre files, Lustre striping, and in order to not to let the I/O ruin the load balance, you need to have dedicated I/O ranks, or even if the I/O is pretty simple. So at this stage, does anybody have any questions on this part? So use your mic or write it to the box. This is not the case. Feel free to ask them later on the comment box of the YouTube recording, or sending direct email, or ask them on Twitter, for instance. But so if no comments or questions at this point, let me summarize the whole webinar series. So first, this is not a summary per se, but a kind of a separate observation is that there's a couple of easy steps that every single HPC user should be aware of, and that is likely to benefit all HPC applications. So the first step number one is that pay attention how you build your programs. So find the best performing compilers and good compiler flag spotters. The step number two is that if there's a library that can do something for you, resort on it rather than trying to make your own room. It's kind of an home room version of something. So employ tuned libraries wherever possible. There's a lot of things you can tune on an HPC environment, ranging from MPI, how MPI does things, to how file system works. So pay attention, spend some time in finding good settings for the Lustre parameters, MPI parameters, and so on. And the last step is that remember that I/O is always a pain for parallel applications. So minimize it by not checkpointing too often, not asking the output you don't need, and so on. Just trying to minimize the and pay attention how and what you do in terms of file I/O. And the take-home messages in general, what comes to performance engineering and code optimization, is that of course the application performance does matter. So it's benefit of you getting faster, you did things done faster, other users as they are sort of no wasted resources, and the service provider, meaning the supercomputing center, just because of we would like to maximize the impact of one installation. However, before optimizing writing faster code, profile the code and identify what's the real reason for, or what are the sort of real performance considerations. So do not optimize while you code, but just optimize it, get it working, get it correct, and then profile it and see whereabouts in the code you should be taking a look at. And the proverb goes that premature code optimization is the root of all evil. Then the serial optimization part, so really the code optimization, as discussed on the second part of the series, is that that's really mostly about helping the compiler to optimize more. And the ingredients for good serial performance is good cache utilization and the using of these vector instructions. And scalability, like discussed a bit earlier, is that that's sort of an established but most of it is being established on when the algorithms and the data structures has been designed. And in order to improve it, you may have to do pretty intrusive changes for the code. There were some minor tricks that you can play on rank placement and so on, but in order to really target for the largest computers, or even this kind of intermediate computers like SISU and now upcoming systems, you must be ready to start tackling this. So it should be an ongoing process on finding better ways of writing things down such that the supercomputers are being all the ranks available are being harnessed as in an efficient manner. And well, that's it, folks. This is what I have had in mind. But just a final remark that don't stop here. So try to apply this stuff, what we've been doing in this webinar series. For instance, there's the last part of the optional lab session to be done. And yeah, I understand that the webinars cannot be related to the this cannot be completely exhaustive set of presentation, just a glimpse on many things or the general idea. And there are courses run by CSC that will put these things that we've been touching here into a bit more into a concrete fashion. So, for instance, the advanced parallel programming and the advanced threading and optimization course coming up on the winter and springtime will be something if you're interested in this. So go to csc.fi/training for finding more information on those. And if you feel like traveling the other training, the other training centers by Brace, then CSC, providing a lot of different kind of courses on HPC programming, code optimization, and so on. So go to the training portal of Brace and see what are the things available there. And then I can still, if somebody has something to comment or ask related to the whole webinar series, let me know. And then in any case, I would like to thank for your time and attention, and hope that this has been at least somewhat useful. And like I said, don't stop here, but start applying this stuff. Thank you, over and out.